Okay, I hope I'm audible to all the students who are attending this lecture. We start with a new chapter in stats today. This is called as joint probability distribution. This is a very important chapter in your course, and it's also of a good weightage in the exam. It comes with a good weightage in the exam. Okay, so formally this is chapter 5 of Devor. Okay, so first let's start with the definition. We have till now we have discussed about the probability density function or probability mass function of only one random variable. But now we have two random variables. So now we will be defining the joint probability mass function. Okay, so let's write this definition. Let capital X and capital Y be two discrete random variables. Let capital X and capital Y be two discrete random variables defined on the sample space delta of an experiment. Then the joint probability mass function, mass function P of X comma Y is defined as P of small x comma small y is the probability that capital X takes the value small x and capital Y takes the value small y. So X and Y are two discrete random variables defined on the sample space delta of an experiment. The joint probability mass function P of small x comma small y is the probability that the random variable capital X takes the value small x and the random variable capital Y takes the value small y. Okay, let's write a note. Probability, the joint probability is always greater than equal to 0, and now since there are two random variables, I will be using double summation. Since there are two random variables, I will be using double summation. So summing up over x, summing up over y, the sum of all probabilities has to be equal to 1. Okay, so I hope all students have understood this. Second point, let A be any set, let A be any set consisting of pairs of xy values. Then the probability that the random variable x comma y belongs to the pair A, belongs to the set A, is summing up over small x comma y belonging to the pair A P of x comma y. Suppose I define A as set consisting of all the pairs of x comma y. Then probability that the random variables capital X comma capital Y belong to the set A is double summation small xy belonging to capital A P of xy. Now, when we actually do numericals, you will be able to understand in an even better way. Right now, these are just statements, but when we do numericals, you will be able to understand it in a better way. So I hope till here it's crystal clear to everyone. We have just defined the joint probability mass function. P of small x small y is the probability that the random variable capital X takes the value small x and the random variable capital Y takes the value small y. The joint probability P of xy will be greater than equal to 0. The double summation, if you sum up P of xy over x and y, it will be equal to 1. And if you take any set A consisting of pair of xy values, then probability that a pair lies in the set A is double summation xy belonging to the set A P of xy. Now let's do a numerical. Let's do a practice question. So a large insurance agency services a number of customers who have purchased both a homeowner's policy, and an automobile policy. From the agency. For an automobile policy, the choices are $100 and $250, whereas for the homeowner's policy, the choices are $100 and $250. The choices are, let me correct myself, the choices are $0, $100 and $200. Suppose an individual with both the types of policy is selected at random from the agency's files. Let capital X denote the deductible amount on the automobile policy and let Y denote the deductible amount on the homeowner's policy. And we are given the joint probability table. X and Y. So X takes the values 100 and 250. Y takes the values 0, 100 and 200. And the probabilities are given to us as 0.2, 0.1, 0.2, 0.05, 0.15 and 0.3. The question asks us find the probability of 100, 100, probability of Y greater than equal to 100. So let's read the question. A large insurance agency services a number of customers who have purchased two types of policies, homeowner and automobile policy. If you purchase a automobile policy, then you have to pay either $100 or $250. If you purchase homeowners policy, then you can pay $0 or $100 or $200. Suppose an individual with both the types of policy is selected at random from the agency's file, and X denotes the amount deducted on the automobile policy, and Y denotes the amount deducted on the homeowner's policy. You are given the joint probability table. You need to find these two values. So what is the probability of 100, 100? It is the probability that X takes the value 100 and Y takes the value 100, which is how much? X taking the value 100, Y taking the value 100. What's the probability? 0.1. And what is the probability that Y takes the value greater than equal to 100? Y takes the value greater than equal to 100 means X taking the value 100 with Y taking the value 100, or X taking the value 100 with Y taking the value 200, or X taking the value 250 with Y taking the value 100, or X taking the value 250 with Y taking the value 200. So Y greater than equal to 100 means what? Sum of this plus this plus this plus this. So this will be 0.1 plus 0.2 plus 0.15 plus 0.3, which will come out as 0.75. So answer for the first part is 0.1. Answer for the second part is 0.75. So I hope all students have understood the definition of joint probability mass function, its properties, and the practice question. Now moving forward to the next part. Let's move forward to the next part, erasing all this. So the next definition for us, we are doing marginal probability mass function. Marginal probability mass function. Okay, so let's write the definition. The marginal probability mass function, the marginal probability mass function of the random variable X denoted by Px of capital X is given by Px of capital X is the summing up of the joint probability mass function but over Y. If you sum up the joint probability mass function over Y, you will get the marginal probability mass function of X. Similarly, the marginal probability mass function of the random variable Y denoted by Py of capital Y is given by Py of capital Y is summation over X, P of X comma Y. This will happen for each possible value of X. For each possible value of X, and this will happen for each possible value of Y. That means when I am finding the marginal probability mass function of X, for every value of X, I am adding all the Y values. And when I am finding the marginal probability mass function of Y, for every value of Y, I am adding all the X values. So I hope all students have become clear. To find the marginal probability mass function of X, you fix one value of X, and for that value of X, you add all the Y values. The probability is corresponding to all the Y values. And to find the marginal probability mass function of random variable Y, you fix a Y value, and corresponding to it, you add the probabilities relating to all the X values. Now again, let's do the practice question on this. So guys, consider the same example as above. Consider the same question of homeowners policy and automobile policy which we just did. Okay, if you all recall, what was my joint probability table was like this: X, Y, X takes the values 100 and 250, Y takes the values 0, 100 and 200. These are my probabilities. Okay, these were my probabilities. You can see that their sum is equal to 1. 0.2 plus 0.1 is 0.3, 0.5, 0.55, 0.55 plus 0.16, 0.7, and 0.7 plus 0.3, 1. Now let's find the marginal probability mass function of X. So marginal probability mass function of X. Suppose I fix a value of X. Suppose I fix a value of X as 100. So what will this be? This will be P of 100 comma 0 plus P of 100 comma 100 plus P of 100 comma 200. So what am I doing? I have fixed the value of X and I am adding the probabilities over Y. So 0.2 plus 0.1 plus 0.2. So this will be 0.2 plus 0.1 plus 0.2, which is 0.5. Similarly, the marginal probability mass function of X when it takes the value 250, it will be P of 250 comma 0 plus P of 250 comma 100 plus P of 250 comma 200. Now that is going to come out as 0.05 plus 0.15 plus 0.3. This will come out as 0.5. So how can I write my probability mass function? So you can see Px of 100 is also coming out as 0.5. Px of 250 is also coming out as 0.5. So therefore I can say my margin, I am writing it on the top right hand side. My marginal probability mass function of X is 0.5 when X takes the value 100 comma 250 and 0 otherwise. This is my marginal probability mass function of the random variable x, which is px of x, which is 0.5 when x takes the value 100 or 250 and 0 otherwise. Now likewise we can find the marginal probability mass function of y. So erasing this, let's find the marginal probability mass function of y. So what will py of 0 be? Py of 0 means when y takes the value 0, so this will be, now I'll be adding up over x. So y is fixed at 0, so 100 comma 0 plus p of 250 comma 0. So this will be 0.2 plus 0.05, which is 0.25. Similarly, py of 100 will be p of 100 comma 100. Again, y is fixed at 100 now. So this will be 0.1 plus 0.15, which is 0.25. And similarly, my py of 200 will be p of 100 comma 200 plus p of 250 comma 200, which will be the sum of 0.2 plus 0.3, which will be 0.5. So what can I do now? So on the top, I am writing the marginal probability mass function of y. So random variable y, this will be py of y, which will be 0.25 when y takes the value 0 and 100 both. So I can write 0 comma 100. When y takes the value 0 or 100, the value is 0.25. And when y takes the value 200, the probability mass function of y is 0.5. And then I can say 0 otherwise. For all values other than 0, 100 and 200, the probability mass function of y is 0. So any doubt to any student in the marginal probability mass function, you can please feel free to clarify it right now. If there are no doubts, I can move forward. So till now we were doing discrete, now we are moving on to continuous random variables. Okay, so since no one has any query, doubt, I can move forward. So let's write the next definition. So our next definition is pertaining to joint probability density function. Whenever you guys hear the word density, automatically it means the variables are continuous random variables, not discrete. Because if they are discrete, we use the term mass function. If they are continuous, we use the term density function. So joint probability density function. Let's write the definition. Let capital X and capital Y be continuous random variables, then the joint probability the joint probability density function f of xy for these two variables is a function satisfying the following, is a function satisfying first property f of xy is greater than equal to 0, the joint probability density function is greater than equal to 0, and second point, integral. Now since we have two continuous random variables, I have two integrations. It's going to be double integration now, from minus infinity to plus infinity, and from minus infinity to plus infinity, f of xy dx dy is exactly equal to 1. So let x and y be two continuous random variables. So they are defined on a real line. They are continuous random variables. Then the joint probability density function f of xy for these two variables is a function which satisfies two properties. The joint PDF f of xy is greater than equal to 0. The second property is integral from minus infinity to plus infinity. Again, second integral from minus infinity to plus infinity, f of xy dx dy is equal to 1. That means area under the curve f of xy is exactly equal to 1. We are using double integration because now we have two random variables. Okay, let's write a note. In particular, if my set of x comma y is such that x lies between a and b and y lies between c and d, you can think of it like a rectangle. Think of it like a rectangle which is being formed where x lies between a and b, y lies between c and d. Then probability of x lying between a and b, y lying between c and d, where x and y are continuous random variables, is integral x going from a to b, integral y going from c to d, f of xy dx dy. So the definition I had given, in that we were going from minus infinity to plus infinity, that was a general definition. But specifically, suppose I define a rectangle. Okay, suppose this is my graph. Suppose this is my graph, x-axis, y-axis. Suppose my x goes from a to b, and suppose my y goes from c to d. And this is my rectangle. It's a closed figure, and at the same time x and y are continuous random variables. Then probability that x lies between a and b and probability that y lies between c and d is nothing but the area of this rectangle, which is nothing but integral from a to b, integral from c to d, f of xy dx dy. So I hope all students have understood this definition. Let's do a practice question on this then, if it's clear to everyone. Let us do a practice question. A bank operates both a drive-up facility. A bank operates both a drive-up facility and a walk-up window. on a randomly selected day, let x denote proportion of the time that the drive-up facility is in use, and let y denote the proportion of the time that the walk-up window is in use. Walk-up window is in use. We are given in the question the joint PDF of the joint probability density function is given as 6 by 5 times x plus y square for x lying between 0 and 1 and 0 otherwise. The question asks us find. So the question asks us the following: verify that f of xy is a legitimate PDF. And second thing, find the probability that neither facility is busy more than 1/4 of time. Neither facility is busy more than 1/4 of time. So let's solve this question. Okay. For f of xy to qualify as a legitimate PDF, f of xy should be greater than equal to 0. You can see that clearly. 6 by 5 times x plus y square. Guys, corrected. This is x plus y square. X plus y square is greater than equal to 0 for x lying between 0 and 1 and y lying between 0 and 1. So the first property is met. F of xy is greater than equal to 0. Second thing is, second property is, this is the first property. Second property within part A, integral. Let's calculate integral from 0. This is the second property I'm writing first. The second property is that integral, double integral from minus infinity to plus infinity dx dy should be equal to 1. Now the function is defined from 0 to 1. So 0 to 1, integral 0 to 1, 6 by 5 x plus y square dx dy. So guys, how will we do this integration? First, let us integrate it with respect to y. So integral 0 to 1, if I integrate it with respect to y, one of the integration sign will go. So this will be 6 by 5 times. If I integrate x plus y square, this will become xy plus y cube by 3. And I will run this from 0 to 1. So, and I will also write dx. Or let me write dx afterwards. Let's first solve this. This becomes 6 by 5 times. Let me put 1 here, y as 1. So this becomes x plus 1 by 3. And if I put 0, the whole thing becomes 0. So now I only have x, so I will be integrating with respect to x. So this will now become integral from 0 to 1, 6 by 5 times. Now I integrate with respect to x. So x ka integral is x square by 2 plus 1 by 3 ka integral is 1 by 3x. Running it from 0 to 1. So again, now since I'm integrating, this sign will go. So this will be 6 by 5 times 1 by 2 plus 1 by 3. I am putting 1 here minus. If I put 0, everything becomes 0. So this will be 6 by 5 times 5 by 6. 5 cancels, 6 cancels. What do I get? 1. So I have shown that integral from 0 to 1, 6 by 5x plus y square dx dy is exactly equal to 1. That means it is a legitimate PDF. So we have shown that f of xy is greater than or equal to 0 because 6 by 5x plus y square is greater than or equal to 0. Okay. We have also shown that integral 0 to 1, double integral 0 to 1, 6 by 5x plus y square dx plus dx dy is equal to 1. First, you integrate with respect to y, keeping x constant. Then you integrate with respect to x. This is how we are doing. Now, let us answer the second part. The second part is asking us, find the probability that neither facility is busy more than 1/4 of the time. Neither facility is busy more than 1/4 of the time. So that means what are they asking us to calculate? In part B, they are asking us to calculate, find the probability that x takes the value less than or equal to 1 by 4. It means they are asking you that x lies between 0 and 1 by 4 because it should not be busy more than 1/4. 1/4 means 1 by 4. And y also lies between 0 and 1 by 4. So this will be integral 0 to 1 by 4, integral 0 to 1 by 4, 6 by 5 x plus y square dx dy. I will now have only one integration sign. I'll integrate this with respect to y first. This becomes xy plus y cube by 3. I will run this from 0 to 1 by 4. So this becomes 0 to 1 by 4, 6 by 5 times. Let me put y as 1 by 4. So this becomes x by 4 plus 1 by 4 cube. So 1 upon 64, and 64 into 3 is how much? 192. So 1 upon 192 dx. So this will be integral 0 to 1 by 4, 6x by 20 plus 6 upon 192 into 5 is how much? We can just check 192 into 5. 960. So you will now integrate this with respect to dx. This will come out as 6x square by 20 into 2, 40 plus 6x by 960. You will run this from 0 to 1 by 4. You will get the answer as 0.0109. This is something you can cross check at home. Okay, so this is where I stop in the lecture today. We have done the concept of joint PMF, marginal PMF, and joint PDF. In the next lecture, we will talk about marginal probability density function. So this is where I stop. We will start with the assignment for probability now in the next lecture.